Just to provide you some relation between the previous Andrei talk and mine, in the previous talk, Andrei was mainly showing you the real cases, complicated cases of running the tests in the browsers, like flaky tests. So it was mainly speaking about the usage of tests in browsers. That means it was showing some client-side stuff. And I will be right now talking about the server-side stuff. That means the environment where these potentially flaky tests could be run. So my name is, again, Ivan Krutov, and today I will be talking about the browser automation infrastructure. So a few words about me. Being software developer during the last decade, my main experience is related to Java and Golang programming languages. My main activities during the last more than 7 years are called with the buzzword DevOps. That means that I'm creating and maintaining various infrastructure. And one of the biggest projects I'm working on is a big Selenium cluster. So how big is this cluster? Compared to a typical Selenium grid, having 50 browsers and executing 10,000 browser sessions per day, my cluster has more than 5,000 browsers and executing 2.5 million browser sessions per day. These browsers are distributed across 5 data centers. The average load is about 4,000 requests per second. The traffic is more than 2 gigabits per second, and this cluster is certainly working all the time. So this cluster has all popular browsers and platforms, including last 10 versions of Firefox, Chrome, Opera, all versions of Internet Explorer, Microsoft Edge, Android emulators running on the real hardware servers, iOS simulators running on Mac Minis, and for some teams, we also have real devices, phones, and tablet PCs connected to the same cluster. So some of you could also be knowing or using some of the tools we're working on, including Selenoid, which is an open source implementation of Selenium protocol running browsers and Android emulators in Docker containers. Also Moon, an implementation of Selenium protocol running everything in Kubernetes cluster. We also have a solution called Moon Cloud, which is basically a Moon cluster running in your preferred cloud platform. So if you have any questions related to one of these tools, don't hesitate to ask me right after the talk. So Andrei was previously showing the browser automation pyramid, and we've seen that there is a small part of very important tests, which are called end-to-end tests. And they are very important because, in fact, running tests in real browsers seems to be the only way to check that your web application is working on the user side in the same way that you are expecting to be. And however, running such end-to-end tests is a very expensive stuff. So first of all, such tests are usually slower than other types of tests. For example, slower than unit tests, and we've now seen a real example that 900 end-to-end tests can run like 10 times slower than 9,000 unit tests. Also, such end-to-end tests require more time for preparing a tested environment. So for end-to-end tests, you may need to launch a virtual machine or a container with a tested copy of your web application. Such tests usually require more effort and experience for their maintenance. So for example, in case of browser tests, you may need to constantly maintain in accurate state so-called CSS selectors. You know, these are expressions allowing you to find elements on the web page. Such tests are usually consuming more computing resources. For example, one browser running in parallel usually requires 1 CPU and 1 gigabyte of memory. So from one point, we know that end-to-end tests in general and browser tests in particularly are very important. But however, we also know that these tests are usually more expensive. They require more resources to run them. And because of that, your browser automation infrastructure that you are using for running such tests should be, first of all, reliable, should be easy to deploy, should be easy to scale. That means you should be able to easily add more computing resources when you need to run more tests in parallel. It should consume computing resources, that means CPUs, memory, disk, and so on, in an economical way. This browser automation infrastructure should be uniform. That means that you should be able to run this infrastructure both in a big cluster being used by the entire browser test automation team, and also you should be able to run this infrastructure on your local machine for debugging your tests. And certainly such browser automation infrastructure should support all popular browser automation technologies that are being used right now. So let's now just walk along these requirements and try to understand whether it's possible to how to say, to have infrastructure that will have all these traits. So first of all, let's talk about reliability. I think you know that Selenium right now is a worldwide browser automation, de facto worldwide browser automation standard. And the most popular implementation of Selenium protocol is called Selenium Grid. So currently, the stable version of Selenium Grid is called Selenium Grid version 3. And I think most of you already know that if you try to run your real tests using Selenium Grid, sooner or later you will face one of instability problems. So your tests will can easily become unstable. So, for example, you can encounter this so-called Selenium window focus problem. That means that if you try to run your tests in parallel in several browser windows, sooner or later your test cases can become flaky. And this is because usually in modern operating systems, only one window can have so-called focus, you can see on the picture. And on the pages, usually there are elements that depend on whether a current browser window has focus or not. So for example, in this picture, we have a green button that becomes just white in case when your browser window has no focus. And because of that, if you run several tests in parallel, depending on whether your browser window has focus or not, your test will pass or fail. So because of that, they are flaky. So one day, your Selenium infrastructure can simply stop working at all. So for example, at the end of the day, you can accidentally just open the browser settings, and for example, type incorrect proxy server connection settings there, save, and then you leave the office. So the next day you arrive and you can see that your tests are simply not working at all. And because of that, a few accidental clicks in the browser settings can completely stop your testing conveyor. Sooner or later, you will also understand that it's pretty much difficult to have several versions of the same browser being installed on the same machine. So for example, having Firefox 82 on your machine, it's rather difficult to have, for example, Firefox version 83. This is because in modern operating systems, software is usually being installed using package managers, and such package managers are usually allowing to have only one version of the application. So if you try to install Firefox 83, you will see that the previous version will be automatically removed. So there are also several similar instability issues with Selenium Grid, and a deep investigation of all these issues shows that the majority of such issues could be solved by providing an efficient isolation between browser processes. So they are caused by the lack of isolation between browser processes. Certainly, in order to solve this, you can launch every separate browser process in a standalone virtual machine. However, this is not so efficient because virtual machines are consuming a lot of resources and are slow. So a much better solution is using containers. And inside every container, you should have everything needed to launch your browser tests. So for example, you need to have a Nix server. That means an application allowing you to show, to launch graphical applications like browsers. A respective WebDriver binary. That means an application that translates your Selenium test commands to browser-specific commands. Certainly, you should have a browser installed to the same container, and also some additional stuff like fonts, encodings, and so on. So everything you need to correctly display the pages in the browser. Usually, such containers should be launched and stopped for every separate test case. And unfortunately, currently stable Selenium grid implementation just doesn't have such feature. It doesn't allow you to launch browsers in containers, for example, in Docker containers. However, currently there are several other solutions allowing you to do this. So first of all, we have an open source solution called Selenium, which is a set of extensions for Selenium grid, allowing you to run tests in browsers. The only issue with this solution is that it was abandoned approximately a year ago. The second solution is called Selenoid. That's a completely separate implementation of Selenium protocol using Docker to launch browsers. And the third solution is called Moon. That's a solution allowing you to launch containers, to launch browsers in containers in a Kubernetes cluster. So we can see that standard Selenium grid is not really a reliable solution. However, we can see that there are some other solutions allowing you to provide a reliable test execution. So now let's talk about the ease of deployment. First of all, let me show you a good example of how an easy to deploy solution shouldn't look like. So that's a picture from official Selenium Grid 4 documentation. So you can take a look on their website, and you can see that here, instead of 2 components that we have in Selenium Grid version 3, I think you know that Selenium Grid version 3 has only 2 components, a hub and a node. Here, you can see that we have now 6 components. So that's more complicated, and that's not an easy to deploy solution. Don't do like this. A truly easy to deploy solution should be a single, like a single box, a single black box, being also deployed in a container. And this black box should be using some container API to launch containers with browsers. So when your test is requesting a browser from this black box, this black box will simply send a request to the container API and launch a container with a requested browser version. And then your tests are executing this container. So when your tests finish to work, this container is automatically removed, thus leaving your host machine operating system in the same state it was before actually executing your tests. So currently, there are 2 popular container execution environments in the world. The first one is called Docker. I think most of you should be aware of this solution. And the second one is called Kubernetes. So we will now be comparing these solutions and their efficiency. So first of all, Docker. Docker allows you to start and stop containers on one machine, on one hardware server and one virtual machine. So you can start containers, you can stop some running containers, so you can do stuff like this. Kubernetes, contrarily to Docker, it can also certainly stop and start containers, but the main difference is that you can do this on an unlimited set of hosts. So for example, you can start on one host, on the second one, remove on one host. And the main feature of Kubernetes is that it can automatically distribute your requests for launching new containers on top of these hosts. You can analyze how many, for example, CPUs and memory you have on each host, and it will just find a slot for a new container on one of the hosts. So that's the main difference. Now let's talk about the ease of scaling. So as I said, scaling here means an ability to easily add more computing resources when you need to run more tests in parallel. So if we first of all talk about Docker, we will see that in case if you need to add more computing resources to your cluster, you will certainly need to manually launch more virtual machines or manually just take hardware servers, and you will need to manually install Docker on each of these servers. And in case when your tests are idle, these servers or virtual machines will continue to run. So there's no built-in feature to automatically grow and shrink depending on your load. In case of Kubernetes, we have a feature called automated scaling or just auto-scaling. That means that your cluster can shrink or grow depending on your load. And usually in big cloud platforms like Amazon Web Services, Google Cloud, Microsoft Azure, DigitalOcean, and so on, Kubernetes cluster is running on top of one or several virtual machines. And in case when your browser tests require more browsers, this cluster will automatically request to launch more virtual machines from the cloud platform. So when you stop running your tests, when you don't need so many browsers, your Kubernetes cluster will automatically downscale. That means shrink after some idle time depending on your cloud platform. So usually it's something like 15 minutes. So, and now let's talk about the economical resources consumption, because usually in companies, the overall browser infrastructure cost, this is the overall browser infrastructure cost that determines which solution will be used by the company, because all normal companies are certainly counting their money. They want to be as efficient as possible. And if we now compare Docker and Kubernetes, we will understand that in case of Docker, you can have many times the situation when you are not launching your tests, but your computing resources are running, and thus they are just consuming your money. So for example, in the real world, usually the majority of automated tests are being launched during the work days, from Monday to Friday. Sometimes people are launching their tests at night, but rarely they're running their tests, for example, during the weekend. That's a rare situation. They're not running tests 24 hours during the weekend. That's rare stuff. And because of that, so far as Kubernetes provides you this auto-scaling feature, that means it grows and shrinks depending on your load. It allows you to economize a lot of money because of that. And because of that, currently, a lot of big companies, like, for example, I don't know, Google, who initially created Kubernetes, or Hewlett-Packard, or Dell, or Amazon, are using Kubernetes for launching their production services, because it allows them to economize a lot of money. So, and returning to Selenium, a truly efficient fault-tolerant cluster in Kubernetes can look like this. So, in idle state, you can have only 2 virtual machines with a Selenium solution running in 2 separate data centers in Kubernetes. And because you are having to separate Selenium replicas, you certainly need to have a fault-tolerant load balancer just to be able to automatically distribute your Selenium session requests on top of these hosts. Usually, such load balancer is provided by your cloud platform. So that's in idle mode. And these virtual machines with a Selenium solution are rather small. They're not consuming a lot of computing resources. But when you request to launch your browsers, because of auto-scaling, your Kubernetes cluster will launch more bigger virtual machines having more computing resources that will be used to launch your browsers. And certainly when you stop launching your tests, these big virtual machines will be removed by Kubernetes. And because of that, usually you will have two types of payments in such cluster. So the first part of your payment will be a permanent payment for the load balancer and these small virtual machines with Selenium. And the second part will be a variable payment for the computing resources for launching your browsers. And this second part will certainly depend on the way you are launching your tests. So if you are not launching a lot of tests, you will not be paying for these computing resources. So if we now have like some theory related to how a Selenium cluster could look like. So let me now demonstrate how it could look like in real life. So hope it will start right now because everything is really slow on my machine. Sorry, it's a bit slow. My computer is just not responding. Do we have any questions? Oh, something is opening. Okay, let me show. So first of all, I will be showing here for those who are who don't have a lot of experience with Kubernetes. I will be showing here that launching your own Kubernetes cluster, for example, in a cloud platform, seems to be an easy task. So for example, here I'm demonstrating how to do this in Google Cloud, but you can do this in any cloud platform you wish. So here, first of all, I'm specifying some name for the cluster. I'm in the respective Google Cloud Kubernetes section. And the main information I need to provide the number of nodes. That means the number of virtual machines that will be running in the cloud for our cluster. So here you can see that by default we will have 3 virtual machines, and now we will be configuring this automated scaling feature. That means we will be specifying how many how cluster can grow when we need more computing resources. So in this case, I will specify 5 nodes. That means that our cluster will be able to grow up to 5 virtual machines. Now we are specifying the size of these virtual machines. So for browser automation, we usually recommend taking bigger virtual machines, for example, having at least 4 virtual CPUs. So now I'm just clicking on Create button, and I will just need to wait for some time for this cluster to be created. So if now we take a look at the list of the virtual machines, we will see that virtual machines are launched. And we can list the so-called Kubernetes nodes with the kubectl client. So now I'm demonstrating that it's rather easy to deploy any application to Kubernetes, because currently there is a well-known package manager for Kubernetes, which is called Helm. And for example, right now I will be deploying Moon to Kubernetes using Helm. In order to do this, I only need to first of all have Helm being installed in my machine. Then I will need to add so-called a Helm repository. That means a web service that provides you machine-readable instructions, allowing you to install any application. These are like Debian or RPM packages that you are installing to your operating system. And so here I'm adding a Helm repository. I'm fetching the latest information about available packages. Then I'm creating so-called Kubernetes namespace. That means like a project in Kubernetes, allowing you to assign available CPUs and memory for such project. And the last thing, I'm just installing the application. So as you can see, I'm only using four simple commands, and you can just copy paste them in order to obtain a running Selenium cluster in Kubernetes. So that's really straightforward stuff. It can be done in 5 minutes, for example. So now, after installing the application, I can check that we have this service running in Kubernetes cluster. So I'm just checking that currently I have 2 containers, or more correctly, pods, running in Kubernetes. So the last thing I will need to do before actually launching the tests, I will need to get an IP address or a domain name to specify in my Selenium code. So in order to do this, I'm getting the information about the services running in Kubernetes cluster. And currently, you can see that there is a service with type load balancer. And here we need to wait some time, for example, 30 seconds, for an external IP address to be assigned by the cloud platform. So if we now issue the same command one more time, we will see that an IP address was assigned. So now we will be using this IP address to run our tests against this cluster. So first of all, we will demonstrate that you can use this IP address to see a well-known user interface. So I think those of you who are using Selenoid, for example, have seen a lot of times this user interface. And now I'll be running a demo test. So I'm showing you that our IP address of the cluster didn't change. And now, instead of showing some real Selenium code, for example, on the previous talk, we were mainly seeing some Java code. Here, I will not be showing you any Selenium code. I will be instead, I will be using a binary that will emulate Selenium tests. So I just implemented a binary which is open sourced to the GitHub, and this binary is a Golang application having only several flags. It's a browser name, browser version, the number of tests that are launched in parallel, because we will now emulate launching a lot of tests in parallel. And the last flag is a Selenium URL. So this test is doing very simple stuff. It's opening our website and it's taking a screenshot. That's it. So we will now launch this command, and we will now check that the screenshot is taken successfully. So first of all, we are launching this command, and we only run one test in parallel just to check that our cluster works as expected. So I'm just typing a standard Selenium URL by using our IP address. I'm launching this command. This command is requesting Chrome 87. And we can now open a respective screenshot file and check that a screenshot of the website was taken. So that's just a screenshot of our website. So now we'll demonstrate how the autoscaling feature works. So what will happen in case if we request to launch a lot of tests in parallel against the same cluster. So first of all, I'm showing you that we still have 3 virtual machines running in the cluster, 3 nodes in terms of Kubernetes. And I will now use just the same command, but instead of running 1 test, I will request to run 50 tests, for example, in parallel. So I'm launching this command, and I can see that 50 tests are now executing in parallel. And now we will, first of all, take a look at the list of the pods, that means containers, being executed in the cluster. You can see that there are a lot of containers, exactly 50. Some of them are in the pending state. That means they are waiting for computing resources. We can see that currently we still have only 3 nodes. That means 3 virtual machines for running this test. And these tests, you can see that they still continue to run. And after some time, usually no more than 1 minute, you will see that your cloud platform automatically added more computing resources to the cluster. So right now you can see that we have now 5 nodes. So one of them is not ready. The second one is ready and serving our browser for 2 seconds. And here tests are still running. So after some time, your tests will finish. And after approximately 15 minutes, see that your nodes were automatically removed by Kubernetes cluster. So now let's talk about the uniformity. So the uniformity means that you should be able usually to launch the same browser automation infrastructure on both in both a big cluster being used to run your stable tests, being used to run, for example, your regression tests, so doing your usual work. But you also need to be able to run the same infrastructure on your local machine, because usually test automation engineers are developing new test cases, and some of them are not stable, are not tested, and you need to be able to experiment in a local machine. So we've now seen that you can easily deploy infrastructure to a Kubernetes cluster remotely, but is it possible to do the same stuff on the local machine? Let's now take a look at the ways of getting a Kubernetes cluster on your machine. The most complicated way of getting a Kubernetes cluster is launching it manually. This is what is usually being done by dedicated teams of DevOps engineers who are working in big companies. And these DevOps engineers are reading Moon documentation or Kubernetes documentation thoroughly, and they are deploying everything manually on top of a set of hardware servers or virtual machines. So this is too complicated. The second possibility is using a cloud platform. That's what we've seen right now on the video. And in both cases, you can use a resulting Kubernetes for launching any production application. So both cases will work. And the third possible way is using a standalone tool called Minikube. So Minikube is just a binary that you can download from the GitHub. And this binary allows you to launch a local Kubernetes cluster on your machine. And certainly, you can use this tool to launch browser automation infrastructure in the Kubernetes cluster. So let's now take a look at the real demonstration how deploying a local browser automation infrastructure could look like. So hope now the video will open faster. Yep, it's opening. It's opening, but it's still very slow. Okay. So the first thing we are going to show here is to install Minikube. So as I said, Minikube is just a binary that you can download from the GitHub. So we are going to respective repository. You are going to releases page, and you're just downloading a binary for your platform. So here I'm showing everything on Mac, and because of that, I'm choosing a binary for Darwin architecture, because Mac is a Darwin architecture. I'm just downloading the binary and saving it to a directory where all executables usually reside on a Mac. I'm giving execution permissions for this binary, and I'm just checking that it's just a command that I can execute. So I'm obtaining a command like this. Now I am installing the second tool, which is called kubectl. We've already seen it in the previous video. That's a command line client for any Kubernetes cluster. That's also an open source stuff. And you can easily install it just by typing install kubectl in the search engine, and you will immediately find the instructions on how to install it for your platform. So here, I'm just using the same approach. I'm getting a URL for downloading this binary, and I'm just executing the same command. I'm just downloading the binary. I'm saving it to the directory with executables, and I'm giving execution permissions. So just the same stuff. Giving execution permissions here. So having these two tools, we are now ready to deploy a browser automation infrastructure to our local machine. First of all, let's start a Kubernetes cluster here. So in order to do this, we need to issue only one command, minikube start. And this command will do all the rest of the work automatically for you. It will download all required dependencies and launch everything itself. So after several minutes, you will have a Kubernetes cluster running on your machine. That's really straightforward stuff. And you can see at the end of the output that this command automatically configured our kubectl to point to this local cluster. So if we now list the nodes of the cluster, we will see that it's pointing to Minikube. So now we are ready to deploy a browser automation infrastructure to our local cluster. And here I'm showing another way of deploying this infrastructure. So we can do this, for example, by using so-called raw YAML manifests. So in order to do this, you need to clone a repository from the GitHub, and you need to apply only one command. So you just clone a repository. You go to this repository, and now you just apply one more command. You just apply a YAML file from this repository using a ready-to-use command. So this command is doing pretty much the same thing we were doing with Helm. It's just creating several objects in Kubernetes cluster. And after executing this command, we will see that we've got just the same state. We've got two containers or pods with Moon running in our local cluster. So the last thing we need to do in order to start working with this cluster, we need to launch so-called minikube tunnel. That's a command allowing you to access everything on your local host. That's to be able to open everything on local host. So we are launching this minikube tunnel, and now we can open the same graphical user interface in our browser just on the local host. Okay. So we've now deployed just the same browser automation infrastructure on our local host. So that was the demonstration how to deploy the same solution on the local host. And now the last thing I would like to show you today, I would like to talk about supporting multiple automation browser automation technologies. So previously, today we were mainly talking about Selenium. However, right now, during the last 2 years, several other browser automation solutions became popular. And Selenium was initially created in 2004 at the time when the majority of web applications mainly consisted of a lot of HTML with some small inclusions of JavaScript, and all these pages were mainly rendered on the server side. So currently, we are living in the world of single-page web applications, and because of that, there is an issue with Selenium. There are some important features, testing features, that are simply missing in Selenium, and that prevent single-page application developers from efficiently testing such applications. So, for example, in single-page web applications, it's very important to be able to track network activity on the page, because a lot of operations are being done in the background using AJAX requests. Also, you should be, for example, able to subscribe to various events in the JavaScript code. You may want also to directly modify the DOM tree, the CSS styles, and so on. So this is just because a lot of work, sometimes a half of the logic of your entire web application is being executed on the client side. And because of these missing features, people just noticed that all these features are already present in so-called Chrome Developer Toolbar. I think most of you all have already seen this toolbar in the Chrome browser. And internally, this toolbar is using a protocol to interact with the browser. So this toolbar is a standalone web application using a protocol to interact with the browser itself. And knowing this, a very good idea came to the mind of test automation engineers. We could simply use the same protocol for interacting with the browser, but from the code. And this is how a new generation of browser automation solutions appeared. So the first of these solutions is called the Puppeteer. And Puppeteer was created by Google. And initially, that was just a Node.js library for interacting with the browser using this protocol called Chrome Developer Tools protocol. Initially, Puppeteer supported testing in the Chromium family browsers only, but right now it also has experimental support of the Firefox for interacting with the Firefox using the same protocol. Another very popular browser automation tool right now is called the Playwright, and this tool is being developed in Microsoft. So Playwright, compared to Puppeteer, from the beginning, provided the way to automate do automation in three popular browser rendering engines. That's the Chromium family rendering engine called Blink. That's the Firefox rendering engine called Gecko. And that's the rendering engine being used for the Apple browsers like Safari and Safari Mobile, which is called WebKit. And also, compared to Puppeteer, Playwright is not a JavaScript-only library. Currently, there are implementations for Python, Java, and C#, and probably several more implementations. So this emerging technology seems to become a real concurrent technology for Selenium. And it's becoming more and more popular. So let me show you that you can also use these new technologies using just the same cluster. So in the same infrastructure, you can launch in parallel both Selenium, Puppeteer, and Playwright tests. So let me quickly show you how it looks like. Let's wait for the video to maximize. Because it's dramatically slow. Okay. So first of all, I'm showing you how to launch a Puppeteer test. In order to launch such tests, we are creating an empty directory. We are installing this Puppeteer library using standard Node.js tools, Node.js package manager, for example. We install Puppeteer. Now we will create a simple test that will be do just the same stuff we were previously doing with Selenium. So it will also open the website and take a screenshot. So we are just going to copy paste an example of code from the documentation, but you can also do this, copy an example test from the Puppeteer official documentation. Just here, just to have an example. So we are copy pasting an example test. We are creating a .js file, and the only thing we need to change here, we just need to replace the host where we are actually be running our browser. So here I will be launching everything on the local host in my local cluster. And here I'm also specifying the version of the browser I would like to launch my test against. So I'm launching the test. I'm checking that I have a tunnel running. I'm launching the test. And I will now simply check that the screenshot was taken by this test. So we can open the screenshot and make sure that we've opened the same web page, but using a Puppeteer. Now I will do the same stuff using the Playwright test, and I'm doing very similar sequence of actions. First of all, I'm installing Playwright. I'm using a bit hacky way. I'm just adding a variable to not download the browser binaries because they will be running in containers. We don't need to download these binaries. Here, I'm creating a JavaScript test. As in the previous example, I'm just copy-pasting an example from the documentation, but you can take, as I said, an example from the Playwright documentation too. That's really standard Playwright test. So I'm just specifying a host where we will be launching our browsers. Here, I'm launching everything on the local host. Okay. So and now after saving my code, I'm launching the test, and I will simply check that a screenshot was also taken by this example Playwright test. So that's it for the video. That's it for the video. So, and to conclude, at the beginning of my talk, we've introduced rather strict requirements for the browser automation infrastructure, and you can see that simply satisfying the requirements is really possible. So efficient browser automation infrastructure is possible, and please don't use efficient solutions for browser automation infrastructure. And usually at the end of my talk, some contact information where you can just ask any questions related to one of the tools we are working on, or any question related to browser automation. If you have, there is a YouTube channel here, for example, where you can see a lot of browser automation we provide. So that's everything I wanted to tell you today. Thank you very much, and let's now take a look at your questions, if any. Okay. Do we have any questions? How Moon configures how many pods should be run on one node? Is it configurable at all? It's not Moon responsibility because how many pods should be run on one node depends on how many computing resources you have. I mean, for example, one browser consumes 1 CPU and 1 GB of memory. If you have only 4 CPUs on the node, Kubernetes will be able to launch only 4 containers. And if you request to launch one more, Kubernetes will probably choose another node where you have free computing resources. So this is Kubernetes that will automatically distribute all the stuff across the nodes. Let's check another chat. There was a question for the previous talk, I think. So any more questions? I don't see a lot of questions. Edgar's, I hear. Hello. Edgar said that he could disappear for some reason, so probably he will now appear again. He said that sometimes this application is freezing. This meetup, yeah, it's here. Edgar, can you hear me? Okay, he's nodding. It seems that we don't have more questions, so probably we could do a short. We disappeared again. We could do a short break and let the third speaker to do his talk. So just type. I will just disconnect right now.
Oh, can you hear me now?
Let's.
Can you hear me now, Ivan?
Yeah, I can hear you, but you're constantly disconnecting from the service.
Yeah, I couldn't understand. Do you hear me previously, and therefore I was resetting my camera. So, but you hear me now, good?
Yeah, I can hear you. So what I was trying to say that it seems that we only have one question. By the way, there is the second one. The rule of thumb is to use. Just for a second. The rule of thumb is to use one browser per one pod. Yes, the rule is to use one browser per one pod, just because we need to launch a separate container for every browser, as I said, to provide a first-class isolation between browser processes. So if we try to run only several containers, several browsers in the same container, we will start getting the same issues with, for example, a window focus. I don't know, with the cache or cookies and so on and so forth. So this is the reason why we are launching one browser in the pod. And there is also a sentence here saying that pod can have multiple containers run. Yes, that's correct. However, how would I say? For example, you may want to have video recording. And in case of Kubernetes, usually video recording software is a separate container. It's being run in the same pod, but it's a separate container. So from the simplicity point of view, it's simpler to run every browser in a separate pod. That's an answer. So I think that's it. I don't see any more questions.